इधर तो नहीं है this one is not here. Ah, how many connected page are there?
3 watching. 4 watching.
Hello everyone, welcome to the live session for analog electronic circuits, and I hope you are following the lectures as they are coming live, and I hope you are working on the assignments as they are being revealed to you, and please keep up the good work. I have a few questions from your side already in advance. Some of you have posted questions in advance. So I will start by answering these questions. So first of all, the first question that has popped up is that some of you are having difficulty in understanding hybrid parameters, their conversion, cascaded amplifiers, and the low frequency model. Now, first of all, this hybrid parameter. So there are four kinds of two-port parameters, right? Four different varieties of two-port parameters. There is H, that's the hybrid parameters. Then there is Y, Z, and G, which is the inverse of the hybrid parameters. And these are all interconvertible. Okay. So, for example, Z parameters treat a two-port network as an impedance. So from all sides you will see impedances. If you push an ampere of current into port 1 when port 2 is an open circuit, then the voltage that you get at port 1 is Z11. Right? So that's the kind of two-port network that we are talking about. So Z parameters are there. Similarly, there are these hybrid parameters. The hybrid parameters are mixed up. So some terms are impedance. So H11 is an impedance, H22 is an admittance, and H12, H21, these are both dimensionless. Okay, so the way to remember this is that in a BJT, I2 depends on I1. Okay, so that's how you remember it. So in a BJT, I2 depends on I1, which means that the way you write it, it's going to be written like this. Right? It's a little hard to remember the hybrid parameters. But if you remember that I2, or rather IC, is beta times IB in a BJT, then you can remember the hybrid parameters. This is really IC. Okay, if you remember it this way, then you know how to fill it in. So since it's hybrid, therefore it's going to be mixed up. So this one is going to be V1 and not I1. I1 is over here, and this one is going to be V2. Okay, because it's mixed up. Now you just have to plug in the parameters. So these are called the hybrid parameters, and clearly V1 is equal to H11 times I1 plus H12 times V2, which means that H11 has units of ohms and H12 will have units of no units. right? Because volts is equal to volts. Similarly, I2 will be H21 times I1. I is equal to H21 times I, so H21 is dimensionless, plus H22 times V2, so H22 will have units of Siemens or 1 by ohms. Okay. Now in a BJT is where the hybrid parameters are used most of the times. In our course, in our analog electronic circuits course, we have not covered BJTs at all. There's a reason why we haven't covered BJTs at all. The reason is that BJTs are more or less, we are done with BJTs. Just like we are done with the age of vacuum tubes. Similarly, we are done with the age of BJTs. The BJTs are out of the market. I mean, you can still buy BJTs. You can use BJTs in the lab with discrete. You can use discrete BJTs to do many interesting things. However, in a general, if you are going to be making an electronic circuit, it is very, very unlikely that you will still be using BJTs. You will be using MOSFETs. So that's the reason why we have not been using BJTs at all. Okay, so we have to pause a little bit. मोटा कर दे. Okay, so sorry about the interruption. They wanted to fix the screen for there was some resolution issue. Anyway, so we have not been studying BJTs at all. BJTs are where the hybrid parameters are used the most, and typically in a BJT, instead of calling it H11, you are going to call it HIE, and H12 is called HRE, which happens to be equal to 0 for a BJT, and H22 is called HOE, and H12 is called HFE. So these are the nomenclatures for the BJT, and that's that. Okay, so it's a two-port network. You treat the small signal model of the BJT as a two-port network with these parameters, and then that works out to something like this. So it pretty much works out to the model of the BJT. So that's the base, this is the emitter, and this is the collector, and I've got HIE ohms over here and 1 by HOE ohms over here if you want to have it as ohms. Otherwise you can leave it as Siemens as a conductance, and then this is HFE times IB, this particular current, where IB is over here. So this is the small signal model of the BJT, or you can treat it as a two-port network, whatever you want to. All right. So this is as much as I would like to talk about hybrid parameters. You can convert between H parameters to Z parameters. Look up any circuit theory book. There are explicit formulations to do that. However, you might not need to do all of that. Cascaded amplifiers. So basically, you can convert from the H parameter to any other. So all right, the cascaded amplifier is where you put two amplifiers one after the other, right? And This is your common source amplifier, right? And this will have a gain of minus GM times RD in parallel with RO. And then you put another stage. So that's your cascaded amplifier. Two stages. You can have many such stages. And then right, so the gain of the first stage is minus GM1 times RO1 in parallel with RT1, and the gain of the second stage is minus GM2 times RO2 in parallel with RD2. Now this works very nicely for a MOSFET. It doesn't work so nicely for a BJT, mainly because in the BJT there is a loading effect. In the MOSFET there is no loading effect. The gate of the MOSFET does not take any current. So this current is zero in the MOSFET. So it's nice and clean and you don't have to bother about any loading problems. In the BJT there is a loading problem. The gate, the base of the BJT also draws current. But then you know how much current it draws. It draws current. I mean, we just discussed the BJT. The BJT has a resistance, an input resistance, HIE, right? So HIE is the input resistance. So that resistance you have to place over here, and that is going to modify the gain of the first stage. So instead of RD1, you are going to see RD1 in parallel with HIE, and that's all. There is it. Okay. Next question that I have in front of me is if the subject is sufficient for GATE EC examination preparation. Well, it might not be sufficient. You will have to read a little, you will have to think a little more, right? However, uh, my hope in this course is to be able, I mean, what I have been trying is to help you to think. If you are able to think, then that is good. That is certainly something that is going to help you with your GATE EC examination preparation. I mean, GATE EC has many other topics other than analog circuits, right? As far as analog circuits is concerned, this does not cover the syllabus fully. However, this does cover a large part of the syllabus. It doesn't completely cover the syllabus. Right. Um, there is a question about the Norton theorem. The Norton theorem is applicable for a linear circuit. Then why are we using the Norton equivalent circuit for the MOSFET, which is non-linear? Okay. So this is this is a very basic question, right? This question should have come a long time back uh, to us. So it's like this, that analyzing nonlinear circuits is very hard. Okay, it's so hard that we don't want to do it. We just do not want to analyze nonlinear circuits because it's too hard to analyze. All right, we are scared. Now, given this premise, and also given that you are learning how to be engineers, what do engineers do? Engineers always try to find an easy way out. Okay, look, that's life, right? Engineering involves trying to find an easy way. Now we are faced with this difficulty that the MOSFET is non-linear, and it's so non-linear. Actually, it is so non-linear. Really, it's so non-linear that we don't even have equations to describe it. Right? You can do a PhD just trying to predict how a MOSFET is going to perform. So whatever equation you have learned in this course, K into VGS minus VT whole square, all of that is wrong. Okay, that is just a zeroth order approximation. It's not even a first order approximation. Okay, it's a very bad model for a MOSFET. So MOSFET modeling itself is a huge topic where so many students are doing PhDs, so many academics are spending their whole lives trying to model MOSFETs. Alright, now given this premise, right, the MOSFET is so nonlinear that we don't want to analyze the nonlinear circuit. So what we have been doing, what we have learned to do is linear circuit analysis. This is something that we have learned. Okay, the Norton theorem, the Thevenin theorem, these are all applicable for linear circuits, not for nonlinear circuits. We know how to analyze linear circuits. We don't know how to analyze nonlinear circuits. We don't want to analyze nonlinear circuits. It's so hard. So therefore, what has come up is something like this, that we know that the MOSFET is taking some current. Suppose this is my circuit. Okay, suppose this is my circuit. We know that the MOSFET has a certain characteristics. Okay, this characteristics is so hard to predict that people are doing PhDs. Alright, so let's not bother about what equation this characteristic follows and so on. We don't know. The x-axis is VDS and the y-axis actually and the y-axis is ID. Alright, now what you do is you observe the circuit at its DC operating point. Okay, at its DC operating point, I see that my drain to source voltage is capital VDS. The current is capital ID. Okay, so I observe it at this operating point. And now when I apply a small signal on top of the DC operating point, the circuit responds with an incremental signal. So when I apply an increment, some additional signal on top of capital VGS, I apply small VGS. So now my total VGS is capital VGS plus small VGS. Then I get something else on the current. So the current also is going to increase, right? The current is going to increase. VGS has increased, so the current is going to increase. Right? It's going to follow a different curve of the same family. Right? Whether VGS has increased or decreased, it's going to follow the upper or lower curve in the middle. This curve corresponds to capital VGS. Alright. And then what is going to happen? VDS is going to decrease because of the increased current. Right? The resistor is going to take a drop. So I will get something like this. Right? Three different settings depending on what is the amplitude of small VGS. Right? So this is going to be the response. Alright, this is small VDS. right? So this is the scenario. This is called small signal analysis, right? So when you start doing small signal analysis, what you effectively do is that you discard all the static operation, that is the DC operating point is going to be discarded, and then you're only going to look at the incremental picture. What is the increment in terms of current through the MOSFET? What is the increment in terms of voltage across drain and source? Alright, that's what you're interested in. And it turns out that the incremental model for the MOSFET is this. This is the incremental model for the MOSFET. Alright? So basically you replace the MOSFET with its incremental model. All the other components remain just as they are, right? And now your circuit, it has become a linear circuit because you're analyzing the circuit only incrementally. If I make a small change on the circuit at the input, what is the incremental current that is consumed? If I make a small change in the input, what is the incremental change at the output? Okay, so as far as that is concerned, now the circuit is linear because all the components are linear. Another way to look at it, to think about it, is using Taylor series. So you know that f of, let's say, ID is some function of VGS and VDS. We don't know what function is. This function is topic of a PhD. Alright, it's a function of VGS and VDS. And this function, using Taylor series, you can write it as such. The DC operating point plus the slope okay, but it's a two variable function, so you need one more. So this is small signal, right? These are the first order terms, and then you've got second order terms in your Taylor series, and so on and so forth. If you now say that small VGS and small VDS are very small, are infinitesimally small, then only the first order terms remain. The second order terms and so on can be ignored. And therefore now the incremental small signal, which is small id riding on top of capital ID, is just these portions, right? Small capital ID goes away. All right. So this is how you linearize the extremely nonlinear MOSFET. And then after you have linearized it in an incremental sense, right? After that, you just do linear circuit analysis and use Thevenin, you use Norton, you use all the linear circuit tricks that you have learned in other courses. Okay. Next question is, in a differential amplifier, common mode input voltage is DC that does not vary with time. Why are we calculating common mode gain? Okay, this is a very interesting question. So you've got a differential amplifier. Okay, you've got two inputs, two outputs, and these two inputs have a bias, have DC operating point. Presumably they have the same DC operating point, right? And that is the common mode input voltage. Okay, but this is not generally true. So if my two inputs are V1 and V2, then the running average of V1 and V2 is called the common mode voltage. And the difference of V1 and V2 is called the differential input. V1 minus V2 is called the differential input. Okay, the average of the two inputs is called the common mode input. Now, for example, if you have two sine waves and they are nicely out of phase with each other, then VCM happens to be equal to 0 because V1 plus V2 is a constant. Okay, or VCM, the common mode, is a constant. Okay, and constant is as good as 0 in the incremental picture that we just discussed, and therefore common mode gain should not matter at all. However, the two inputs need not be perfectly out of phase. If they are not perfectly out of phase, then what is going to happen? Suppose there is a misalignment. There is a misalignment of 1 degree. Alright. Now suddenly you will have V1 plus V2 by 2, which is not equal to a constant. Okay. If misalignment is more, as these two phases are more and more misaligned, you will have more and more common mode input. Alright. So it is to handle these situations that we need to have low common mode gain, because we don't want our circuit to respond to an average that is changing with time. Let me give a practical example. Suppose I have a signal and I have an interferer. Alright, suppose this is a communication system. Alright, you've got a signal, you've got an interferer. Now V1 has an interferer, V2 has the same interferer. Okay, so V1 is a good signal plus an interference. V2 is another good signal plus the same interference. The common mode signal will have V1, V2, the average of V1 and V2, which hopefully is 0 or a constant, and it also has the interference. I don't want my amplifier to amplify the interference. I want it to amplify the signal. Okay, so this is why common mode gain should typically be as close to 0 as possible. Alright, next question is what is the definition of small signal? Small signal, the definition really is infinitesimally small, as small as you want it to be. If you're not happy with how small it is, if it is producing distortion, if the non-linearity is too much in the circuit, then make the signal smaller. That is small signal. Is a subtractor an inverting or non-inverting amplifier? So I don't clearly understand this question. A subtractor is inverting. Subtractor is a subtractor. It's not an amplifier at all. I mean, you've got two inputs. One goes to the inverting input of the op amp. The other goes to the non-inverting input of the op amp. Okay. There is a question about suggesting reference material that describes a generic method of finding transfer function of an electrical network between all possible pairs of driving points, output points for voltages or output branch for current just by having a look at the electrical circuit. So follow my advice. Use Norton's theorem as far as possible. If you want to do it by inspection, use Norton's theorem, right? Especially if it's a MOSFET based circuit. I hope you are referring to a circuit which has MOSFETs in it. Use Norton's theorem, right? Or in other words, the voltage gain is going to be output impedance times the transconductance. So use this and do it step by step. Find out the output impedance, find out the transconductance. Right? We have discussed how to find out output impedance in many different ways. Right? How you should memorize a couple of formulae, actually two good formulae. If you memorize, you are going to be in very good shape to find out the output impedance quickly. One, what is the impedance when you're looking from the source? The other, what is the impedance when you're looking from the drain? Right? So if you memorize these two, you can apply these two formulae repeatedly and quickly compute what is the output impedance. Then GM, the transconductance or the short circuit current, also you can compute easily if you remember those two formulations. And if you're working with a BJT, then you will have to memorize one more formula. There's an additional level of complexity in the BJT, that is the base, right? So you have to memorize. So first of all, you have to generalize the formula a little more. So you have to place another resistance at the base, right? So you place one resistor at the base, one resistor at the collector, and then you find out what is the impedance looking into the BJT from the emitter. The other is you place a resistor at the base, place a resistor at the emitter, and find out what is the impedance you see looking in from the collector. And then there is a third that you have to memorize, that is you place a resistance at the base, at the collector, a resistance at the emitter, and look in from the base and find out what is the resistance that you see looking in from the base. So now you need to have three formulae. In the MOSFET, looking in from the gate makes no sense, it's always infinite. Okay, so you are helped in that way. Okay. Then there are a few more questions. Relation between bandwidth and response time. If the bandwidth is larger, the response time is going to be lesser, right? Bandwidth has units of hertz. So seconds is in the denominator. Response time has units of seconds. So if bandwidth is more, they are going to be inversely related. It's very simple. Just by looking at the units, they are going to be inversely related. You have to be a little careful in saying this. You also have to use something called Q. Typically, what happens is when you talk about a filter, we are not really now talking about our MOSFET circuits. If you talk about a filter also has something called quality factor, Q. Remember delta, so bandwidth divided by center frequency, that is called the Q. So if the Q is higher, bandwidth might be more. Okay, bandwidth, you have set a certain bandwidth, but if the Q is higher, then it's going to ring more. The response is going to go up and then come down, and the response is going to take a long time to settle, even though the initial response is very fast. So When you say response time, you have to really be a little more specific. You have to talk about settling, right? Or is it just the initial rise? The initial rise depends on the bandwidth. The settling also involves the quality of the circuit, the quality factor. If the Q is high, it takes more time for it to settle. It rings more. Okay. Next question I have is uh, how is FinFET technology different from MOSFETs? So FinFETs are a variety of MOSFETs. Okay, they are a variety of MOSFETs, but they have a front gate and a back gate, or in other words, they have two gates instead of one. It's almost like our MOSFET, where one gate is the gate and the other gate is the body. So you've got a front gate, you've got a back gate. Okay, so the model for the FinFET is exactly the same as the model for our MOSFET. It's just that you have to now analyze with two gates instead of one. As far as the technology is concerned, it's no longer a planar technology. It's constructed in this fashion, where you've got one gate over here and the other gate over here. It's not sitting on a plane. It's 3D. So this particular course is not about technology. This particular course is about circuit design and analysis. So we won't talk about how the FinFET is made or how it looks. We are going to talk about how it is going to be modeled. So how it's going to be modeled is exactly the same way as the MOSFET. Instead of one MOSFET, you use two MOSFETs because there are two gates, right? So there are two gates. The drains are common. The sources are common. So you draw it as if you've got drain is common, source is common. You've got a front gate, you've got a back. That's all. Okay, the rest of it is just the same. Which is a good book that has analog electronics problems? You can refer to, there is a book written by Razavi on analog electronics. What is it?
Microelectronics.
Microelectronics, yes. Fundamentals of microelectronics. There are many other books, right? There are many other competing books, but that's typically a good one. I have one more question which says, what is the relationship between permeability and permittivity? Or rather difference between permeability and permittivity. So permeability is magnetic permeability and permittivity is electrostatic permittivity. So one is epsilon, the other is mu. So one comes when you are discussing magnetic fields, the other comes when you are discussing electric fields. So one comes when you are discussing inductors, the other comes when you are discussing capacitors. That's the difference between permeability and permittivity. Uh, Permeability is because of magnetic domains and permittivity is because of polarization in the insulator. Okay, so any other questions? Quickly shoot your questions on the interface, on the chat interface. There was one question on MTech programs. So this is uh, uh, diversion. But yes, there are MTech programs in VLSI in all the different IITs and as well as in IISc. And there is an active push in making these MTech programs uh, very good. So the government helps us with by sponsoring these programs through various forms of software tools, lab support, and so on and so forth. Uh, the MTech programs in VLSI are actually very, very popular. You would know more than me because your peers uh, you would be talking more to your peers, right? So you would know better how popular they are. I really am not in your seat, so I wouldn't know, but I believe that they are very popular. At IIT Delhi, we get some of the best students that come out through GATE, and we also have at IIT Delhi we have industry sponsored MTech programs in VLSI where you get internships and which generally lead to absorption in these companies. Um, so these are also some of the very popular MTech programs in India. It's called VDTT. VDTT is the program. You have to come through GATE. Um, any other questions? Please drop in a question on the chat stream. Okay. All right. So uh, looks like there are no other questions. So we are. What else? You have something specific for me to talk about, or I can just talk about analog circuits in general. So analog circuits is generally speaking a very uh, niche area. Uh, why I'm calling this niche is because this is an area of expertise where you need to understand a lot of different things. You need to understand device physics, a little bit of device physics. You need to understand electromagnetics. You need to understand communications, uh, mathematics, control theory, mathematics. You need to understand circuit theory. You need to understand power systems, power electronics. Right nowadays, power electronics is the next new frontier for analog electronics, and you need to understand all kinds of things, including heat, uh, thermal engineering, thermodynamics, uh, magnetics, all over the place. So an analog circuit designer is typically all over the place. Okay. As a result, uh, I mean, because you have to be an expert in all these different areas, uh, what ends up is that an analog circuit designer is a prized possession of an organization. So if you join a company, let's say, or you join some IIT, or you join a company, then the company is going to value an analog circuit designer far more than a digital circuit designer. In any case, the digital circuit designer's job is easily replaced by a computer. I hope you know that, right? A computer can replace the job of a digital circuit designer quite easily, right? Just have to set the parameters right and it's going to do the job. The computer is going to do the job. So there is no need to pay so much salary to a digital circuit designer. However, the analog circuit designer brings different kinds of values into the company all over the place, right? So he understands thermodynamics, packaging, heat, power management, power electronics, power systems, transmission lines, microwaves, RF. He's all over the place, right? So his value to an organization is far, far more than any one other person. All other people are less valuable than the analog circuit design. You understand? So analog circuit design is therefore something which is a fantastic career choice. If you choose analog circuits as your career, it's a fantastic choice because you can't be fired, right? I mean, you bring so much value to an organization that they just can't fire you. Okay, everyone else can be replaced, not the analog circuits can. So I just want to point this out because this can change your opinion about what should be your career path. So that's why I wanted to point it out. Okay, in the meantime, there are a few more questions on my screen. Where to practice analog circuits for gate? I don't know. Don't know. What is the difference between AC load line and DC load line? Um, I don't know. Is there any difference? It's the same. The load line is the load line. I don't think there is any difference between AC load line and DC load line. Is there any possibility to do analog IC design as hobby? No, you can't do IC design as a hobby. You can do IC design as a career, not as a hobby. Integrated circuits are expensive, right? And I mean, the cost of silicon is very, very expensive. It's we call it real estate. So it's actually far more expensive than actual real estate because it's pure silicon, right? So typical costs are for 1 square you will have to pay 5 or 6 lakh rupees to get circuits made on 1 square millimeter. All right. So I don't think you can pursue analog IC design as a hobby. You have to pursue it as a career. You can do discrete analog circuits as a hobby, no problem. Right there, you purchase circuits off the shelf, you purchase components off the shelf, and you can assemble your circuits. But IC design can't be a hobby. Uh, yeah. So fabrication is very expensive, but is analog IC design possible as a hobby with hard work put in open source tools? Yes, it's possible. So you can use open source tools and put in hard work and you can design circuits. That's absolutely fine. So as far as software is concerned, yes, I mean, I would like to encourage you to use open source tools. So one of the common simulators is ngSpice. It's actually a very good simulator. Please use ngSpice to do your analog circuit simulations. ngSpice. All right. You can use this to do your analog circuit simulations. And then in addition to ngSpice, there are other layout editors like Magic and so on, with which you can uh, do layout. But I think as if you're going to look at it as a hobby, you should use ngSpice. Spend time with it, get the circuits up and running, then only think about fabrication at a much later point of time. All right. So I think that was good. We can stop now and wish you all the best in your endeavors and wish you all the best for the exam that's coming up soon. And thank you. Thank you very much. Okay.
I think